Hi, everyone, and welcome to the seminar. We're pleased to have Dr. Yogesh Rathi as our speaker today. Uh, Yogesh is an associate professor at the Brigham and Women's Hospital, Harvard Medical School. Broadly, he works in the areas of signal processing, image processing, statistics, control theory, machine learning, and computer vision to solve inverse problems in medical imaging. His current research focus, and he has several, and I'll just mention two things, is on developing protocols for ultra-high resolution diffusion imaging in a clinically viable setting, so clinically feasible scan time, combining both acquisition and reconstruction, and to develop methods for harmonizing multi-site diffusion MRI data from several large databases. So Yogesh and I have known each other for a while. We first met here at UCLA for a summer school when we were graduate students on mathematics in brain imaging, and I actually see Paul Thompson in the audience. So it's like full circle. We're all together again. So Yogesh, he obtained his PhD from Georgia Tech in EE, where his research looked at solving this particle filtering problem on differential manifolds with shape priors. So particle filtering, for those of you who haven't heard this, is an elegant statistical method for tracking dynamic states across time. So while that was an elegant theoretical formulation and a contribution on paper, Yogesh went ahead and developed it further into an equally elegant software implementation in a tractography algorithm, which he now uses for precise targeting of deep brain stimulation type settings and TMS settings in obsessive compulsive disorder, OCD, Parkinson's, and depression. What he's recently known for is his method for doing DTI harmonization. And some of us here have used methods like Combat, for instance, for integrating multi-site data. In his talk, Yogesh is going to tell us why there's a better way of doing multi-site harmonization at a signal level instead of a statistical level for DTI data. So let's welcome Yogesh.
Thank you very much, Shantanu. So thank you so much. For inviting me and giving me this opportunity to talk about the work that we have been doing for the past few years now. So I'm going to talk today about harmonization, and I'll try to put forth some points about potentially why it is a better idea to do harmonization at the signal level. But there is always a give and take, and so there is obviously some requirements that need to be satisfied if you do this. But I'll come to this as I go on, and I'll be happy to take the questions maybe towards the end, so I can cover all the things that I would like to cover. So I'll just outline of my talk why harmonization, and then harmonization versus data pooling, what I tend to call it. Then I'll talk about retrospective harmonization, which means that data has been already acquired and now you need to harmonize between scanners. And then prospective harmonization is where I talk about harmonization where you're still planning the study, you have the ability to send out traveling subjects, and so harmonization in that context. And then some open challenges and questions. So let's start with the very, very fundamental basic idea of reproducibility. So on the same scanner, same subject, how much variability on a modern 3D scanner do we expect? So as you can see here, this is essentially within scanner, same subject, but not much really. In 2 to 4%, maybe here and there in white matter, and maybe a little bit more in the gray matter, 10%. But within the scanner, not much of variability. So this is on whole brain, generalized, even on the generalized fractional anisotropy, you also see the same sort of results. So why do we see variation even within the scanner? So shouldn't it be exactly the same? I mean, you go, it's the same person. I scan myself, I get out and I scan again. Why should there be any difference? So a few reasons. First of all is differences in shimming, which happens when you kind of try to make sure that the magnetic field is constant across the brain. Then there are also biology-induced variations, pulsation effects. You're always obviously breathing, heart is beating. Those effects also show up. And then there's also impact of the time of day. So let's say you did the first scan in the morning, the second in the evening, there will be some differences. And then there is gradient performance variations. So if you're continuously running the machine on and on, the heating creates some variation. So this is within the scanner. What about between scanners? So here is some results on taking two or more subjects, same subjects on different scanners. Here in this case, it's Siemens versus GE. You can see one of the coronal slices. This is percentage difference in FA. It's 10% in white matter, 20% in gray matter, just roughly speaking. And then CSF, anyway, it's not that much material, but it's the differences are a little bit larger. But here, as you can see on the right plot, also we have 3 subjects. The difference between the scanner is much larger versus within the scanner is pretty much the same, as I said before. So why are there differences? The differences between the scanners are what, 10, 20%. So what's the big deal? Why should we even care about that? So the reason is that when you want to investigate differences between healthy and psychiatric disorder subjects, the differences we see are about 5%. I'm sure the audience here pretty much knows and has worked quite a bit on all of these type of things. And you're very well aware this is a pretty standard or typical scenario. You'll see a difference of 5%. This is still statistically significant. On the right, also, you see this is another paper from our group. The differences between swimmers and soccer players. Now, the differences there seem to be really, large, but actually speaking, the difference is only 14% between the groups. So, still, which means that if your inter-scanner differences are 15, 20%, you'll not be able to see this. Here, you can see these things because they are on the same scanner. And when you have many, many sites, this obviously becomes a problem. So here's another example where, if you don't harmonize, this is, FA changes across the ages. This, sort of purple line here, curve here, gives you what is typically expected from what we know so far on single site studies of age-related changes in healthy subjects going from 15 to 75. But if you don't harmonize and you put multiple sites together, you obviously get something very different and not necessarily correct. So these differences between scanners there are additional confounding factors. So not only the magnetic field inhomogeneities, but also differences in the number and sensitivity of the coils, the vendor-specific reconstruction algorithms. Then and these differences between the scanner are not uniform. It's not like one constant number. Things are different. No, they're dependent on the region. They're different on tissue types, as you can see on the figure on the right. Subcortical regions are slightly different than the gray matter, than the white matter. And these differences I'll show a little bit later down the line are present in all frequency ranges in the diffusion MRI signal. And they are very highly nonlinear. So one might say, well, why not just take some phantoms and use them? So as I try to motivate with this one very short slide that you take a physical phantom, it doesn't have the complexity of a human brain. And there is no simple way then to translate changes in the phantom to changes in the brain. How do you map this? So it's much more challenging to do that. So, I think, this is now becomes very obvious why you need harmonization. Obviously, if you have large amounts of data acquired from multiple different sites, you want to pool them all together and answer some really good statistical questions. And so the goal of harmonization is to really remove, or rather not remove, but reduce this inter-scanner variability and make it similar or closer to intra-scanner variability. So you reduce this variability while preserving all the biological differences that we can, and ensuring that, especially in the context of harmonization, you ensure that when you do all of these changes, nothing new, no new data is invented, or no signal is lost, or at least try to minimize that loss. So a lot of work has been done for accounting for scanner differences. So, I think you all are aware about the great effort that Paul and the entire group has been doing with the Enigma software. And that for those who are not aware, you use a z-score at each site and then compare the z-scores across the sites. There might be some confounds if the sample size is small, but might be okay if you have fairly large sample sizes at each location or each site. And there is some assumption about linearity, of these site differences. And it's a great way to harmonize, or rather to combine data. If people cannot share the raw data, which may be the case many of the times, you can only share the derived measures of the derived disease scores because of so many administrative or other hurdles for sharing large data sets. So then there is another method of adding statistical covariates. You add a covariate for each voxel location, and that allows you to capture regional and tissue related differences between the sites. Again, the assumption here is that the site differences are linear in nature. And then there is another method which was reported by Paul. They had data from 3 traveling subjects, and this is a little bit more prospective type of setup, but still, harmonization was performed by looking at 3 traveling subjects. How much was the difference in a given ROI in FA, for example, and then that same correction factor was applied across for all different ROIs across the brain. And this may be okay. 3 traveling subjects may not be enough to capture all of those differences, but perhaps for using a specific measure like FA might be fine. Yet there might be some confounds for large ROIs like the corticospinal tract. It goes all the way from the brainstem to the cortex, and that could be a problem. And then there is recent method called Combat. I'm sure many of you know about it. It uses a voxel-wise additive and multiplicative factor to account for site effects. So in addition to just adding some additive effect, which is what typically, for example, this ROI correction method does, you add a multiplicative factor as well. The assumption being that these factors are driven by, have a prior in terms of a Gaussian and inverse gamma distribution, and which may satisfy many cases. And then there is these methods which we started to work on since about 6 years now, on harmonizing the raw signal itself. And here you use either traveling subjects or match control subjects from each site to learn what are these scanner effects on the raw data itself. The mapping is done, and of course, I'm going to describe this in detail a little bit later. But the mapping is done, at a voxel level, so regional and tissue-specific effects are addressed, and non-linearities in these differences across the scanners can be actually captured. But as I said earlier, there is one requirement for this particular method to work, is that you need sufficient number of matched controls or traveling subjects across the sites. And how much you need, I'm going to address that question down the line, but still you need very good number of very well matched number of controls. The field of harmonization is growing pretty quickly. You can see that with the number of papers that are getting published every few years now, And there has been a competition as well, which I'm going to talk about a little bit down the line. And I just want to kind of categorize the methods into two sort of blocks based on how they are done. So one is these statistical data pooling methods, where you do the statistical analysis at the very end of the pipeline for each diffusion measure of interest. And many of the statistical methods like combat will fall under this category. And then there is the harmonization methods, where a linear or nonlinear mapping is done between sites. It works on the raw data, and as is done before any model is applied to the data, so just right after pre-processing, and allows you to do tractography and all of those things in a very elegant manner, because the data has now been harmonized across sites. You can imagine that if you want to do tractography, you can always do it between sites as well. But if the differences are there, the tractography itself is affected by the harmonization. So it becomes a bit of a problematic comparison to go forward after that. And one of the reasons why I feel that we should do it, the harmonization should be done before, is because we don't know certain things about data pooling, like what is the effect of choosing a particular model, or what is the effect of the noise characteristics on the diffusion measures. How does that affect the harmonization ability? And I'm going to talk a little bit about this down the line. So here it is. What we did was and this is a very interesting experiment, we took 3 different softwares, FSL, MRTrix, and Slicer. We gave them exactly the same data. And these are data from 5 different sites. So you can see the color here represents the different software, and then these are 5 different sites. We did not harmonize here. I'm just talking about what is the effect of software processing. Most of the sites are looking good, whole brain, mean FA looking fine, all the 3. But here is site number 3 is funny. It has very different looking whole brain FA in these set of healthy controls. And so the question is now, if you were to acquire data and run pre-processing with different software at different sites, then there is going to be a problem. And I can show that what will happen if you happen to do that. So this is just motivation to convince people not to do this. Obviously, you should use exactly the same software. One may think, oh, diffusion tensor fitting is the same exactly everywhere. Apparently, it is not. So here is an effect that can happen when using combat. So our goal here was to say, let's find out if we can preserve the effect sizes before and after harmonization, because that is what should happen. When you have some data set, you have 2 groups here. So here it is healthy controls and schizophrenia subjects. As you can see on site number 2, everything is pretty much preserved. I mean, there is a purple line, which is the color that shows what is the effect size before harmonization. X-axis the Cohen's D, telling you the effect size. And then the orange is the difference after harmonization, but when the data was processed using only one software, FSL, for all the sites. And then the green is if you were to use different software for different sites. Now, with site 2, things look fine. I mean, more or less, the effect sizes are preserved. But site 3, something very different starts to happen, as we expected. And now what you can see is that suddenly, for example, the right SLF, which had no statistical difference between the groups, starts to see significant difference if you use 2 different type of software. And so many other things that you can note here that are happening. And this is another example here, differences between male and female. Again, site 1 looks pretty good. Site 5 has something that is going on here. Especially, I will note that before harmonization here, some of the fiber bundles, and this is on an atlas, some of the fiber bundles had a positive site group difference, and that turned out to be negative after harmonization. So the green and orange line is after harmonization. And even though they don't seem to be so big yet, it is a problem that we saw that, okay, you're switching the direction of the differences. So that is a little bit of a problem when you go and do use some, some of these methods can have. So that's why motivation, try to say, well, let's try to harmonize it before, at the very beginning, where once you pre-process the data, you harmonize, and then anybody can use it for any type of analysis as they would want to, with any type of method, any type of model. So how do we go about doing harmonization? We have site 1, controls or traveling subjects. Site 2, we learn a nonlinear mapping, and I'm going to just very quickly go over how we go about doing it. We first do all the pre-processing. So you match the spatial resolutions, you do Gibbs unringing, EPI distortion correction, motion correction, etc. The typical things we do with diffusion MRI. And then we compute what are called the rotation invariant spherical harmonic features, which allows you to estimate features that are rotation invariant. And then we do a spatial alignment of these features across the 2 different sites. Then based on averages of the 2 different groups, we learn a nonlinear mapping in the signal space, but a linear one, for example, could be in the rich feature space. And then we go back and update our raw dMRI signal at site 1, and then that's how it turns out to be harmonized. So the pre-processing steps, as I said, involves all of the standard ones. We also match the spatial resolution if they are different between the 2 sites. The current software uses 7th order B-spline, as was shown to be one of the best ones in this work. We also use Gibbs unringing, and we match the B values as long as they are within a certain range. If you have different sites with different B values, we map it using a log of the signal. And then the next steps, I'm just going to show you what happens. We take a particular voxel in the brain, and this is what you see there up top is the signal for a particular voxel. And then we fit a bunch of spherical harmonics bases to it. Here is a basis that you can see. And, this is, let's say, it's using all the even order harmonics. So it's because it's a symmetric signal, and then with the sum of the coefficients. And then what we do is we calculate the norm of each of the harmonic bands. So order 2, 4, 0, 2, 4 is all shown up here on the right. And the norm of these are called the rotation invariant features, because no matter how you rotate this signal, these features will stay the same. And this is what you can see how it looks like on an image. So these are ordered all the way from 0 to 8, and as you can see, they're showing different contents, frequency contents. Order 0 is very different from order 2, which is a bit different than order 4, and so on. And each of these order, as you go higher and higher, are higher order frequencies. And as I said, whenever we do some we develop algorithms, we make certain assumptions. And I want to highlight this very strong assumption, or rather an assumption we make is that statistically 2 groups of well-matched healthy controls will not show significant differences statistically. So this is an assumption we make, that if you have 2 sites, and this is for retrospective cases, ideally you would want to do it prospectively, but because the data is already acquired, you still need to get to a point where you can harmonize the data. So you try to match the controls from the 2 sites on all possible demographic variables, age, sex, IQ, etc. And if some possible match is not possible, you regress out that confounding factor. And then, as I said, you do a spatial normalization or registration to create an atlas. And then you learn a nonlinear mapping between these rich features. And once you know how to scale these rich features, you can then appropriately update the signal. And this is about the only slide that has some mathematics or an equation on it. So this is how it works. Here is the signal, the spherical harmonic coefficients, and YL is the basis. And then for getting the new coefficients, you just apply the scaling to these coefficients, and you get you can update your signal. So how does it look on realistic data? So this is data from 2 different sites. This is PNC, the Philadelphia Neurodevelopmental Cohort, and BWH. Both were matched for all possible variables, as I mentioned earlier. As you can clearly see, those 2 sites have very different looking reach features. And this is average over, I think, about 24 matched, 24 controls. They were different slightly on spatial resolution, b-value, and number of gradients. This is another reason why I say that the features, scanner differences are not just linear, they are non-linear. And you can see here for different frequency ranges, the things are very different. And at the bottom is these scale maps. You can see how much scaling is required in each different region. It's very regionally heterogeneous as well. So we said, okay, let's see how well we did with this kind of mapping on our training data set. And this looks more or less okay to us. But here are more compelling results, more clear results, I would say. So this is the effect size before on the PNC data, before and after harmonization. And as you can see, the effect sizes are now preserved in this case. This is for age-related biological differences between groups. And this is on the white matter. And more or less, what you see on the left side is the Cohen's d, and then the right is just kind of categorizing them between small, medium, and large effect sizes. And it's kind of staying more or less the same after harmonization. And this is another example, differences between, again, that was for the males, and this is for the females. And again, the harmonization preserves the effect sizes, which is, I think, one of the important things we wanted to check, that it doesn't add new information or create new information while we do this. This is a comparison between combat and our method here. So what you see on the top is basically before and after harmonization. What was the age? How did FA vary with age for 2 different fiber bundles here? The left IFO and the left SLF, and on the bottom is with combat. So obviously this. Because the combat cannot incorporate the nonlinear changes due to variations in FA over age, it ends up, showing a very different trajectory here. So as I said, we need a well-matched set of controls for our data. So here is what we did to see how many controls we need to match from both the sites. And this is the average or the mean sort of scale over the whole brain, how much the mean and the standard deviation over the whole brain, and x-axis is the training data size. So as you can see, obviously, it converges after about 14 to 16 training data sets, and this is very well matched set of controls. So we typically end up going towards the higher end, so 24 or even 30, to be absolutely sure that we are harmonizing only the site differences and not biological differences. But at the minimum, it looks like you need at least 14 subjects on both sites. This shows pictorially the same thing. As you can see, if your training size is 2, much more, obviously a lot of, errors if you were to only use 2. 12 kind of starts to get better. 16 is pretty decent, except for a few places maybe in the CSF areas. And then 18, it kind of starts to become pretty much uniform errors, meaning 0 error more or less. So now I'll move on to talk about prospective harmonization. In this case, you have traveling subjects. And I think pretty much this is how the harmonization should proceed, ideally in an ideal world, but because that is really truly has very minimal number of confounds. So People have tried to use physical phantoms or traveling subjects to acquire data, and then you learn a mapping between the two sites, and then you use that to apply to the rest of the sites. So for example, here is one example where we could do this. So before and after harmonization, you can see pretty much the differences between the sites are removed. And because these are the same subjects, we can actually measure that very accurately. As far as phantom goes, they definitely have a great role to play to monitor things going wrong, things going, there are software upgrades. Many times I know in our hospital, we sometimes don't even know if people have upgraded the software, and suddenly the images start to look different. So physical phantoms are a good idea to use, especially also if there is a drift in the scanners. And there's a nice study by Timmermans in 2019, where they used this single strand DTI phantom and showed that almost all scanner variables contribute to differences in multiple sites. So coils, scanner drift, bandwidth, software, you can pick variables. And it's very hard to control for each of these things individually, because no matter what, at the end of the day, if you have different vendors, things are going to be different. They can't be made to be the same. And so, but one challenge with this setup is that, okay, you acquired, as I said, you acquired the phantom at two different sites. How do you transfer this to to generalize this to the human brain? It's not trivial. So we started with, in the prospective case, apart from a sort of a competition that was held at MICHI, we also did some experiments where we took the extreme case of trying to harmonize between sites where the magnetic field strengths were different. And one of the reasons is that we had a large number of data, access to a large number of data, about 150 subjects scanned both on 3T connectome and 7T scanner. So we could really do some very good validation about whether the harmonization can actually work in this case also or not. In this particular case, we had used a deep learning model, which is a nonlinear mapping to learn from 3T to 7T, trying to match both the B1000 and 2000 B values data set between these two scanners. And this basically, the graph shows that more or less you need more than 10 subjects for training with this particular type of model. And here is some of the results with that deep learning model. So originally the root mean squared error, percentage error between 3T and 7T was somewhere around 30 to 35% difference in different measures. But with just linear method that I proposed earlier, which is just learning a scale map between the rich features, the differences go down dramatically. I mean, you're getting 7 or 4% errors there. And then if you start using some deep learning models like deep CNN, the differences go down even further. And starts to get closer to the point where it, if you push it, I guess, maybe this is the plateau, but maybe there are methods that can do even better than this to get to a point where it is as if it is between two scanners. And this method we published sometime in MICHI 2018. And this is what you can see here. Now, it's not just important to see the numbers, but also actually visually how it looks. So on the bottom is the difference between the predicted and the actual FA from, I think, about 40 subjects. And on the top is just what the FA looks like. Different methods are shown here. And you can see the cycle GAN, which is a deep learning method. When it learned from 3T to 7T, the difference in FA, and we didn't learn FA, we learned to map from the diffusion MRI signal from 3T to diffusion MRI signal on the 7T. So what we are looking at is FA. So derived measures, while we didn't work directly on them, look to be really pretty much very close. I mean, pretty much 4 to 5% error. And what about fiber orientations? As I said, the fiber orientation should be preserved when we do this harmonization because we're working on the signal. So we looked at look at several different fiber bundles. And what we found is that after harmonization, things didn't change much. We still obtain about 93 to 97% overlap between the tracks, which is pretty good because it is pretty much like scan to scan variations. About 95%, 96% is what we would expect. And so we also participated in this Mushack challenge, which was conducted at McKay. So what they did was, and this is a community challenge, so what they did was they had 15 traveling subjects between two sites. 10 were released to us for training, and 5 they were kept for testing. And the people who ran the challenge tested it on their own. 21 different algorithms participated in this challenge. And you can see this paper that is out now in Neuroimage 2020. Our method was one of the best performing methods. You can see here the results where the average, the absolute predicted error was about 5%, whether it's FA or mean kurtosis. Again, as I said, the data we harmonized was the raw data. The evaluation was done on several different metrics. I'm just putting up 2 here just to show that beyond the DTI model, even the kurtosis measure worked pretty good in terms of, and you can see the names of, you can see more details in this paper, I guess. So that, harmonizing between 3T and 7T and the connectome and Prisma scanners kind of told us that there is a potential to harmonize data despite large differences, at least even though here the differences were in T1, T2, echo time, and so on. But maybe for traditional scanners, like interscanner difference could potentially definitely be reduced or be brought closer to the differences so that side effects can be removed. And so right now we are in the process of doing several large-scale studies. So, we have already, this is part of our R01 grant, where we are harmonizing about 30,000 subjects, but 10,000 subjects from the ABCD data, which was recently released. We started to harmonize it, and the results should be available maybe towards the end of the year on the NIMH data archive. People want to use and do anything with it. And then we'll also, delve on doing same type of harmonization on the human connectome project data sets. It's about 10,000, and then there is the Healthy Brain Network as well. And our goal is first to perform harmonization, and then you will run photography and do white matter clustering, where about 80 or 90 different white matter, anatomically well-defined white matter fiber bundles will be extracted from these harmonized data sets for each of the subjects and put onto the NIMH data archive, of course. And then there will be a web-based visualization where you could log into the NIMH data archive or the NDA. And once you have the credentials, you'll be able to just on your browser browse through these different data sets or download some of the derived measures if you want to analyze specific looking fiber bundles or anatomical categorization of those fiber bundles. So looks like I did run through a little bit through my presentation, but I'm getting closer to the end, but I'll summarize some of the things that we did, and I'll be happy to answer questions as well. So we think that harmonization should be done at the earliest possible stage. If it allows, if you have access to the raw data, do it. First, run the pre-processing in exactly the same manner for all data, and then do harmonization there. That allows you to do modeling, any kind of model-based analysis in the future. Then the prospective multi-center studies, if possible, use traveling subjects so that you remove the confines of having to match these controls, and that the biology will not change too much. Although traveling subjects has obviously the other challenges and issues of logistics. How do you travel? How many travel subjects and how many you need to move? And the other big advantage of doing it at the signal level is that you can perform connectivity studies in a consistent manner across sites, which is probably not possible if you have very different looking site and data. We definitely want to make sure that when we do these kinds of harmonization, you want to check that you're not introducing any new information in the data, for example, new peaks or changing the fiber orientations. Like we did extensive testing, I would say anybody who does new algorithms should definitely check for these. And validation should not only be standard FA or mean diffusivity, but model independent metrics on the raw signal should be also used for validation of the harmonization. And it would be good to characterize how does the harmonization affect noise in your distribution. There are some open questions about data pooling that I'd like to put out there. I think people might be interested to know about that as well. Question is, when you have data sets with very different B values, and the relation, we know the relation between B values and FA or mean diffusivity is nonlinear. So can we really use statistical methods which are linear in this scenario? It's a question to be asked. Spatial resolution could be very different between two data sets. Then partial volume effects will be a problem. So how do we then harmonize linearly between them is going to be a question. Or whether we can use nonlinear methods, then how do we use those nonlinear methods to obtain data pooling in a proper manner? Then the other question would be, what about bias? For example, if you have very small number of controls on one of the sites when you want to do meta or mega analysis, does it actually end up changing anything in your group analysis? How does it affect your group analysis? And then the demographic variables, what if you cannot match them? So those are the things that need to be considered. And yes, basically what if your assumptions are not valid? I think those are the things I would say that we should always be careful about when we use, either when we develop new algorithms or when we use somebody's algorithms. It's important to know what are the underlying assumptions made by that algorithm. Otherwise, sometimes you using it as a black box may not be a good idea. So pushing forward, we are trying to see how we can, look at gross pathology, tumors, MS lesions, and can we capture differences between scanners from 3 to 5 traveling subjects? Will this be consistent across vendors and MRs, versions of MR software? And what about inter-protocol differences? Can we harmonize such scenarios? I think if we kind of address some of these challenges, it might be, this particular setup will potentially be useful for in clinical trial studies when people want to look at pathologies. And of course, we're starting to look, I think this I didn't put here, but this ISMRM, we've started to look at structural MRI images as well to see how we can reduce differences between sites there. And then we're also looking at functional MRI. This is just a list of publications related to this. And I would like to thank all my collaborators, my team at the PNL, and definitely a big thank you to Sohaila, who's really done most of this work. And the software, harmonization software, is available for people to use at this GitHub link. You can download and run it on your setup. And if you have any questions, we'll be happy to answer them. Thank you. And yeah, happy to answer questions now.
Thanks, Yogesh. Great talk. And we'll open up for questions. Just maybe unmute yourself and just ask it already. I see but before we go there, I see a question on the chat by Robert Welsh.
Yeah, that's my question, and actually, I'll follow up with that. So, obviously, one of the issues with diffusion imaging, and you alluded at first, great talk. Really appreciate the talk. It was like super clear, and looking forward to like trying out the software. So, one of the issues with diffusion imaging, or one of the, I mean, it's a reality of physics, is that, and you addressed this, was like the B values. So even if B values are matched, it doesn't necessarily mean that they're measuring the same biological environment because of echo times, right? And so based on vendor and based on gradient performance, you could be probing like different areas. And so even though you might have like your Risch construct, right, and you're matching on that, if you, is that under the assumption though that it's measuring the same biology the same way versus, and with the same sensitivity? Versus if you have a different echo time, you might not see different harmonics, right? So anyway, I'll stop.
Right. No, that's a great question. That's why I think the retrospective is like a band-aid, I would say, to the problem. The prospective is the way to go so that you match on most of the variables you can across the sites. But given what we have with the data that is already acquired, one of the things that the Risch also brings to the table is that it is sensitive to the microstructure. And in that sense, if it is within a certain range, I wouldn't say that you could match Risch features from a B of 1000 to a B of 3000. They're looking at very different aspects of the biology there. But if they are close enough, you might be able to match them. And I think that's what, there are some papers on tissue microstructure modeling from the NYU group where they use actually the Risch type of features to extract features like axon diameter and so on. But again, as I said, it is, as long as it is close and within the range of things that can be measured, the Risch feature will work. But if you're way out, there's no chance.
So if I can have a follow-up, how do you think then we can assess that? Say like I've scanned on like a Prisma that has, either like 80 millitesla per meter per second or 200 millitesla per meter gradients versus I go to a Skyra that maybe has half that. And so if I dial in, like I want to do a B of 3000, right? The Prisma can do it in a much shorter echo time.
Yeah.
Where the Skyra might need to extend that echo time out like 50% more or something like that because of the maximum gradient that it can achieve.
Right. So excellent question. And if I get the sort of gist out of it, what you're asking is, even in prospective studies, how do I pick what to choose? And in case of trying to use in multi-site studies, what should I do? That's a question that is a hard one to answer also, in the sense that it is still, I think so for example, what right now we have, our lab has a U24 grant on exactly trying to figure out these things. The way we have gone, or we are planning to go through this kind of question is, first of all, try to get as many sites as possible on the same type of scanner. So we're trying to get as many sites as Prisma. Well, yes, 70% got there. Now the remaining 30% are there. They're still distributed between vendors and Skyras and Philips and so on. So we're trying, there is no magic bullet yet to say that this is a universal protocol that you can use and this is the exact same B values and spatial resolution you will be able to achieve, because some scanners don't even have multiband. So there's going to be these type of other challenges as well. So what we are doing is we're doing a two-tier sort of system where one tier, majority of the scanners, you get the best you can. The second tier tries to go as close as possible in terms of echo time and spatial resolution B value. But if the higher B value cannot be achieved, then you just discard that and you use only the lower B values, because there is just no way to otherwise do it. I think that's going to be the reality of things, I suppose, because you'll always have something that is 40 millitesla and another thing that is an 80 millitesla or 100 millitesla.
Well, thank you, and I'm very happy that the NIH is funding your research. It is
yes,
definitely
we're happy to.
Yeah, thank you.
Any more questions? Okay, hey, Paul.
Can I ask a quick question?
Absolutely.
So it was wonderful to hear you speak, Yogesh, and I know you and Shantanu have done rather a lot of work since I met you in 2004 at UCLA.
Okay.
So I have a mathematical question for you, and I just learned a lot from your talk. So obviously the main goal of harmonization is when you have collected data from many, many sites. I mean, you want to get rid of any non-biological variability that has to do with the scanner. But you have all these wonderful new methods, and you and Sohail have been working with deep learning, cycle GANs, and so forth. And it seems to me that deep learning could work in partnership with new image acquisition to sort of boost or enhance the signal. Now,
absolutely.
I realize that in your efforts, you're creating a fundamental statistical representation of the signals that anyone is going to collect, and you're splitting it into, basic fundamental geometry and scanner-specific variation. So my question is, I wonder if the entire aggregated data and deep learning models you're computing could be applied to, in a sense, new data to boost, not just to eliminate confounds, but to boost the detectability of certain features that maybe we don't have time to collect the data to resolve. And just your general thoughts on that area.
Yeah, no, I think that's also definitely another area that could be pushed forward. I mean, for example, you could potentially think of acquiring scans where some of the scanners don't really have that sort of bandwidth to really push through all the way, but you could get a lot of data that is within its reach, and then push to get some data that is on the boundaries, and then use some of these deep learning techniques to use, combine these efforts to predict something that is at least maybe a little bit more reasonable, to say that you could still get a reasonable looking image at a p-value of 3000, for example, which probably is out of bounds, or it's extremely noisy for a Skylab. So I think that's a great area to go forward and combine these things to get to a point where you also use these techniques to remove those scanner related differences also, while you're integrating it with your protocol design. Yep, that's definitely a great way to go forward too.
That's so cool. So thanks for a great talk. And thanks again. It's great to be back virtually at UCLA.
Thank you. Nice
so
if
I can add a comment on top of Paul's comment, that reminds me of I'm a physicist, and that reminds me of the Roland diffraction grading machine. So Roland was a physicist 100 and odd years ago, and he was able to make a diffraction grading machine from screws that if you turn the coarse screw that you make on a machine slowly enough, you can make diffraction gratings that are on like the nanoscale or like the microscale, to be able to be sensitive to stellar spectra that, this is 100 years ago, and you're using machines that, or in the machine shop. But if you do it the right way, you can actually get that sensitivity with coarse machines.
That's true. I mean, I think it's those. I guess I would say that even with the existing set of scanners, a lot of the screws, a lot of the knobs have remained to be turned, that you can still use to get potentially whatever sensitivity you need for doing this. Yes.
So how do have you looked at, or anyone else has looked at, how to compartmentalize all this variability from intersite, disease, and so on? And I especially mention disease because in your rich features, and maybe you didn't talk about this, but you're probably doing some kind of alignment. Are you? Can I think it's solving an alignment problem?
Yes, so there is yes, the registration is there. We learn these mapping between the sites on a voxel scale. So you take the data from two of the sites, you align them into a single spatial normalization registration, and then look at each of these sites and look at each of the voxels and say, okay, how much difference am I seeing between these sites that is could be attributed to differences in scanners. And then this you do only on the healthy controls. So you don't do this on the disease subjects.
Okay.
That's why you need this setup where you need the controls to be matched. And then you can apply, once you learn this mapping on the controls or healthy subjects, you apply the same thing to everybody else. And then you're good to go to analyze the data in a pooled manner.
Okay. So then I have a two-part question. So one part is, if you didn't do this harmonization, and if you just did registration to accommodate MNI, how much of the insight variability is accounted for that way? Has anyone actually done some analysis?
Right. So I think there was one abstract, maybe it was HPM or something like that, some maybe a year ago. They said they just do registration, and you analyze the data in that registered space. In our case, we just use this registration to learn what is the mapping, but then we go back to the original subject space and work there. But in this case, they just registered everybody. Naturally, because of the smoothing, the differences go down.
Yes.
That by design that will happen. And so yes, it is helping, but it still doesn't remove a lot. I mean, it accounts for some power portion, because the noise is one portion that typically adds to the variability. So registration helps. And then I think they also did Gibbs on ringing. So, this is, and that added a little bit to it. So these are they do add, but they are very small amounts.
Okay.
And they that's why we do it as a pre-processing step anyway, the Gibbs on ringing.
Okay.
But then when you go, I think the other thing is that if you're looking at two scanners that are like exactly the same Prisma scanners with exactly the same software settings, it might be very close. And in some cases, it might be that you just need registration-based smoothing or something, and it will be done. But most of the time, you'd get Prismas that also have different software versions. Sometimes you have different coil configurations. Instead of 32 channels, you have 16 channels, 20 channels. And then if you go from Siemens to GE or Philips or Canon, then all bets are off, because everybody uses a very different way of reconstructing the data also. So there, I think, those things don't necessarily add too much value.
And then my second part was, you showed the preservation of effect sizes, but that was in controls, understandably. So females, males, and so on. Hopefully, there's no chance of getting rid of disease effects after
right.
Harmonization.
Yeah, I think one of the slide was between healthy controls and schizophrenia. So
so that was compact.
So So we did try that, and I think Sohaila also has a paper in molecular psychiatry on looking at 13, 15 different sites and looking at harmonizing it and looking at how the variations go. So I think, yes, we checked it on multiple different data sets and with disease.
Okay. Cool.
Can I ask one really quick question?
Sure.
Do you have a suggestion for a case where, for example, the controls are not very similar? So let's say a site is scanning kids and another site scanning adults or older people. And you might say, I mean, why on earth are you harmonizing this data? But maybe there's a lifespan study. I don't know the answer to this. It's a tricky one. But do you have a suggestion about what to do with that disparate population?
Yeah, that's extremely hard, I guess. I know this often comes up also, but I think unless there is a way to match the controls from the sites, it's very difficult, because as you say, I mean, even if you look at children at the age of 1 and in children at the age of 5, things are so different. So, and these effects are very nonlinear. We don't know how to characterize them unless you already have a study that has these effects characterized in that particular study for that particular protocol, for that scanner. Those things are very hard to get by. So yes, unless, I think the only way is to have at least 2 or 4 some sort of controls scanned on both places that you can use as a guide to know how much are the scanner differences, and then you just update them.
Actually,
So in some way,
that's such an ingenious solution, because I think your method, because you allow traveling phantoms to help you estimate the signal, that would be something that wouldn't be available for some of these other retrospective methods like Combat, where there's no way to use that data.
Exactly.
And something maybe that got lost in the slides was this works for DTI models and higher order models as well. Right? Okay. Yes, that was not clear. Okay.
Yeah, no, I didn't put too many results there. Only I think there are 1 or 2 results that I put for mean kurtosis or return to origin probability or everything. So we do the harmonization for each b-value shell separately, and then we combine the things together. And so yes, it works out for all possible. Yeah, the other. Okay, I should put one more thing just because you talked about this, is that this particular setup will not work for DSI because we assume that the gradients are on b-value shells. A DSI, you have random set of b-values and gradient directions, and of course you could compute other features, and the overall setup could work, but exactly using the spherical harmonics will not work because by definition they are on a sphere.
Yeah, it makes sense. And you showed a slide of fiber orientation after harmonization. Did you show the result before harmonization? I don't.
Yes. So there was one table there. I didn't show too much, but there were overlapping fibers before and after, and then also there was a table that showed how much % was there before harmonization and how much % was after harmonization, and it kind of matched. I mean, there were not that many differences in the tractography. The tractography, to my mind, is a little bit, in these data sets, was very stable because they are HCP, they're processed really well, the 3T and the 7T regardless, but and they were the same subject, scanned pretty quickly. But if you were to go for, I think there is one ISMRM abstract last year, or there's a paper right now that shows that if you were to look at tractography from 2 different sites from the same subject, sometimes you will see that the corticospinal tract doesn't go all the way through, or it doesn't have all the sort of spread, the fanning structure completely as with the other data. Obviously the same subject. So I think that's where, again, we need to make sure that we, use the methods in a very mindful way.
Can I ask one more question and one more comment? So one of the issues also with diffusion is the gradient nonlinearities. So gradient nonlinearities are fixed in terms of spatial distortion on the scanner, in terms of the scanner actually will correct for the fact that the gradients are nonlinear. However, those gradient nonlinearities are not corrected for inside the B values because you actually don't have a flat B value map across the field of view, but it actually drops off in a quadratic sense. There's this work from Tom Schinaver's group back at Michigan that looked at this very carefully. Your method is, though, correcting basically across a spatial map. So presumably that corrects for that. Have you looked at any of the data to see magnitude of correction with respect to how far away you are from the sweet spot of the magnet, like the center of the true center of field of view? You would expect less harmonization requirement in the middle versus maybe perhaps more on the edges where the different vendors maybe have different gradient nonlinearities.
Yeah, that's some of these things. I think, I mean, we haven't looked at it. I think partly because we didn't collect such specific type of data where the only difference was potentially the gradient nonlinearity related things. It's something to be looked into, I think, to see if you can correct potentially for those things as well. But I would think that yes, the method is more or less a black box in the sense that it corrects for all possible differences that could potentially occur between the 2 sites without knowing which one it is correcting really and how much is the effect of each one of them. But that's something definitely to be looked at, is to say, okay, let's acquire one data where you look at the gradient nonlinearities.
But your method is, though, correcting on a voxel-wise
Yes.
scale, right?
Yes.
So in
Yes.
some sense, your black box takes care of it.
Yes, it does.
Where if I was just trying to do like a simple linear model of, I'm just going to throw things into like, R and throw in a linear model of like site compare, different site variables and all that, that would not take care of that because I'm using like a single correction scalar versus a scalar, like instead of a correction tensor, I'm using a correction scalar, right?
Right.
Great. Thanks.
Yeah.
Thanks again for the talk. It's excellent.
Sure. It was my pleasure.
Any other questions? If not, let's thank Yogesh again for such a wonderful talk. And it's great to, again, give a shout out to Paul. Nice to see you here after a long time. So great, everyone. So see you guys next time in June. And this is the end of the seminar. Bye.
Thank you, everybody. Thank you.
Thank you.